2.6, number 46? Yeah, sure. Okay. So this says find the horizontal and vertical asymptotes of each curve. If you have a graphing device, check your work by graphing the curve and estimating the asymptotes. Okay. So the vertical asymptote we'd assume occurs where the denominator approaches 0, right? So to get the x by itself, we do the natural log. So for the vertical asymptote, we'd be looking at the limit as x approaches the natural log of 5, either from the left or from the right. If either of these is going to equal negative infinity or positive infinity, we would say then that there is a vertical asymptote, right? Now, obviously, we can't do this by direct substitution, but that's okay. This is something we could do by graphing or by inspection. Fairly easily. So 2 e to the x over e to the x minus 5. And then we'll just look at that on the standard window. So I'll do zoom standard on that. So if I look here at, if I do second calc and I do value and I do natural log 5, that's about 1.6, and you see that there's no y value associated with that because that is the vertical asymptote. And from looking at the graph, then the left end is going to negative infinity and the right end is going to positive infinity. So you can do that. Does that feel okay, Mia? Okay. And then for our horizontal asymptote, well, to show it's a vertical asymptote, you have to show either the left hand limit or the right hand limit is going to infinity. Whether it's positive or negative, it doesn't matter. So one of these two would be enough to show that this is a vertical asymptote. You don't need to have both. It doesn't matter if it's going to positive infinity or negative infinity. It doesn't matter. I did both because we're just being thorough. And it wasn't, if we're just going to be looking at the graph, it wasn't much of a hassle. After you got one, you might as well get the other, right? For the horizontal asymptote, we need to be looking at what's happening as the limit approaches positive infinity and negative infinity, because it could have two different horizontal asymptotes. That's possible. Again, we could do this by inspection. It looks like there's a horizontal asymptote here at 2, maybe. But we can confirm that algebraically. Would you like to do that? Probably not a bad idea. So what I'm going to do is I'm just going to multiply the top and bottoms by 1 over e to the x. And the reason I'm doing that is because it's going to get rid of most of my variables, oops, and it's when it doesn't get rid of a variable, it's going to leave me something that I can use I can take the limit with. Oops. Hi. Nico, for you. You're welcome. So let's do the bottom one first, because it's probably a little bit clearer as to what's going on. When I take the limit as x approaches infinity of 2, I get 2. The limit as x approaches infinity of 1 is 1. And the limit as x approaches infinity of 5 over e to the x should be 0, right? Okay. Is everybody cool with that? And hopefully you remember that the limit as x approaches infinity of e to the x is 0, right? That was one of the things that we saw along the way in the chapter. If I do the same thing over here, so this is just 2, obviously. If I try to do the same thing over here, what's the limit as x approaches negative infinity of 5 over e to the x? Here we have a problem, right? Because what's the negative exponent going to do? Yeah, so this is actually going to be equivalent to the limit as x approaches positive infinity of 5 e to the x, right? The negative exponent makes a reciprocal, right? Everybody's okay with that? So basically, what do we have down here in the denominator? So this should be going to 0, which is, I think, oops, we lost our graph there. Does match up with what we're seeing here, right? I have an asymptote here at 0 and another one here at 2. If I knock off the axes here, there you can see the horizontal asymptote at 0. And there you can see the horizontal asymptote at 2 a little more easily. Well, you have like 2 over big, right? That's going to 0. So again, this, what I've written here, like, is not really proper math. I wrote that here so it's easy for us to understand. How would I write this so that it looks more like some proper math? We could bump this out and just call this the limit as t approaches infinity then of 2 over 1 minus t. And then you can use like our polynomial rules, because now it's just a rational function, right? There's no more exponential in it. So if the degree of the numerator is less than the degree of the denominator, this should be going to 0. Is that okay there, Mia? Sure. Now, like I'm going to put the infinities in there to help with our intuition so we don't get bogged down so much in notation. But I'm going to try to go back afterwards and then show you, like, this is the way you'd want, like, a mathematics grader would want to see this, what they would want to see this look like. Or I think even if you had gone straight from here to here. Probably would have been okay on the AP exam. But I think they would have not liked it if you put like an infinity in the equation that had it equal something. Or you did kind of like a direct substitution with an infinity. Is not really proper good mathematics notation. But Mia, are you happy with what we did there? Okay. Victoria, you had a hand up, right?
Yeah, I was going to ask you to 45.
45, which is kind of the same thing, right?
Yeah.
It's actually going to be, I think, a little bit easier because there are no horizontal asymptotes in this one.
How do you know?
I can tell by looking at the degrees. So because the degree of the numerator is greater than the degree of the denominator, there's no horizontal asymptote. You'd have like that diagonal asymptote, that slant asymptote. But that's not something that we care about because it asks only about horizontal and vertical. So, oops. So the vertical wise, I care about when x is at 5 and at 1. And I'm just going to call this f of x. I'm sick of writing this stuff down. So for the VA, we have to look at these pieces. You could. Oh, sure. Yeah. Yep, you absolutely should. Thanks, Mackenzie. Because what do I notice here? So that I don't even need to check. Since it can't be a vertical asymptote, that's like a removable discontinuity, which I would have noticed when I looked at the graph here in a moment, but we can check it right now. So let's try to do this without graphing it because it's certainly doable. So if I'm plugging in 5, approaching from the left, so something a little bit less than 5, I'm basically thinking like 4.9 in my head when I'm thinking about this. I'd have like the top, I'd have a positive times a positive, okay? In the bottom, I'd have a negative. So positive over negative is going to be a negative. Everybody agree with that? And if I have, in the denominator, if I have something just a little tiny bit less than 5 and I subtract 5 from it, I'm going to have a tiny small number in the denominator, right? Or a negative number very close to 0. I guess I should say not tiny small. You know. Everybody's okay with that? So this should be going towards infinity because we have a tiny small number in the denominator but a fixed, like a normal size number in the numerator. Does that make sense to you guys? I could have, but since I looked at the graph for the other one and I want to just talk through how you could do it without having to look at the graph in case you ran, because there are portions. So I'm imagining in my head like a number that's a little less than -5, like 4.9. So if I plug that in up top, I just get some normal size positive number, right? In the denominator, I'm going to get something that's negative and then very close to 0. When the denominator is very close to 0, the fraction gets very, very big. So that's where I'm getting the infinity from. Is that okay? And if I do the same thing for the other one, everything's going to be the same except something a little bit bigger than 5 minus 5 is positive and close to 0. So that should be my positive infinity. And if I wanted to do the HA, let's pretend I didn't notice, or they asked to, like, you know, prove or verify or whatever your result. And I'm going to write it this way. Because that's just the reduced version. It'll give me the same result. The limit will be the same. Mackenzie? I'm sorry, you said something, but it was kind of quiet and you were looking down. Okay, can you, I'm sorry, I couldn't really hear you. Could you speak up a little bit? You're confused? You want to look at the graph? The original? I think either one, it'll give you the same picture, near as you can tell. Oh, that should be a minus. Oh no, +1 is right. But I think either one should give you the same picture, at least until you, like, zoom crazy far in to see the removable discontinuity. And we're just not tall enough. Let's make that, I don't know, 30 or something. There it starts coming in. Is that what you were worried about? Was you couldn't see, you only saw one part of it? Yeah. So it's just really high up there. We could make this 20 and this maybe 50, and we'll should get a decent picture now out of that. There you go. It looks more like a rational function, right? Where here's our vertical asymptote at 5. And then here's our slant asymptote that we'd be expecting, since the degree of the numerator is greater than the degree of the denominator. Although if you tried to do this algebraically, what would I want to multiply here in this case? I would do 1 over x. I would not want to do 1 over x squared, because if I do that, I'm going to end up with 0 in the denominator. So I want to just kind of get the denominator to not have a 0 in it. That's x squared plus 1. That's just the reduced that I multiplied back out. So when we do this, we basically get that, right? So that should be infinite. Now, would I want you to write it that way?
Are they trying to say that?
No, you could just go straight to this, and that would be fine. But the AP people don't like it when you plug in infinities, like you're doing a direct substitution with an infinity. That's bad notation. That's bad mathematics. Even though intuitively, like, that's kind of what we're doing in our head. Mackenzie, are you happy with what I did there? Victoria. And then the same thing would happen down here, right? It doesn't. I guess this should be negative infinity. My apologies. Because limit was going to negative infinity, but. Yes. Yes. So because this limit is not finite, and this limit is not finite, there's no horizontal asymptote. Yes, that's exactly what that is saying. Remember, the definition for a horizontal asymptote was that limit had to equal some L, some real number L. Infinity is not a real number. So there is no L that those limits go to. Does that feel okay? Victoria, you okay with that? A little bit sneaky in that there was no horizontal asymptote there. But ideally, you would have recognized on sight that that was going to be the case, and that would have been much less confusing. But if you didn't, that was kind of a surprising result.
Although vertical asymptote, what are our answers? What do you write?
Oh, it's the VA is at x equals 5.
Okay.
And this would be your justification for it.
Okay. Because it has to equal either negative, infinity, or positive.
Yeah, from one side or the other. Doesn't have to be from both. Doesn't have to be the same on
But
both.
the horizontal asymptote has to equal a number at the end.
Yes.
Okay. And then what would our answers be? Like negative, infinity, or positive?
Oh, your answer is no horizontal asymptote.
Yeah, but let's say for example.
If this was 5, you'd say like y equals 5. And if this one was like 7, you'd say y equals 7.
Okay.
You know, that's all. Elvis, is that a hand?
Yeah, so what happens if the degree of x in the numerator is less than 10?
It'll end up going to 0. So your horizontal asymptote will be at 0. Because again, you multiply by 1 over to get rid of the x's in the denominator. You'll end up with a 0 in the numerator afterwards, which is fine. That's good for us. Sienna? Same section? Sure hope so. Okay. A function f is a ratio of quadratic functions, has a vertical asymptote at x equals 4. So that tells me that the denominator has a factor of x minus 4 in it, right? Has one x-intercept at x equals 1. That tells me the numerator is going to have a factor of x minus 1 in it. X-intercept, x-int. It's known that we have a removable discontinuity at x equals negative 1. So that tells me that I have a factor of x plus 1 in my numerator and my denominator. And it says then the limit as x approaches negative 1 of f of x has to equal 2. Everybody's okay with all of this? All right. And then it asks to evaluate f of 0 and the limit as f of x approaches infinity. What I'm going to do here is start by finding f of x, because we haven't found f of x yet. What can still be going on here? There can still be some constant factor floating around in here. And to find that, I'm going to use this piece. Okay with that?
Why do you know those? That's just like something that
Because the existence of a constant isn't going to change any of the given information that we've built, right? If I have 2 times this thing, it's still going to have the same removable discontinuity, the same vertical asymptote, same horizontal asymptote. But I don't even know that there is a constant on there, but there could be.
So you just always do that.
And I have to check that, and the limit is what I'm going to use to check that. Is that okay with everybody? Okay. So I know that the limit as x approaches negative 1 of f of x is going to equal the limit as x approaches negative 1 of the reduced version of this. And I love that because that I can do by direct substitution. So I know that 2k over 5 is the limit, and that has to equal 2. So k must have been 5. So this is my f of x then. It asks then for f of 0. Well, that should just be -5 over -4, or 5/4. And then b asks the limit as x approaches infinity of f of x. Well, I can see that the degree of the numerator is equal to the degree of the denominator. So that should just give me the leading coefficient of the numerator over the leading coefficient of the denominator. And I'd be done there. What was the most challenging part of this? Building out the f of x and specifically getting there's a constant factor of 5 attached to it. Sienna, did that? You happy with what I did there? Victoria?
How to get k to 5? The last step was 2k.
Yeah, I just solved that equation by multiplying both sides by 5 over 2, which simplifies down to 5. Is that okay?
Yeah.
I just kind of looked at it though and was like, you know.
Okay. So then, how did you get 5 over 4?
I plugged 0 in to f of x. So I have 5 times 0 squared minus 5. That's just -5. And then I have 0 squared minus 3 times 0 minus 4, which is just -4.
Oh, okay.
Right?
I'm
It's okay, you can ask. I skipped those steps. It's okay to ask about it. Right? I just kind of said it and did it. And if you caught what I did, then it was really obvious what I did. And if you're looking at it and you're like, wait a minute, I'm still kind of catching up. I didn't really hear what you said all the way, and what you said didn't register, then that's certainly something to ask a question about, and that's okay. Mackenzie? 14 from 2.7? Okay. Says, if a rock is thrown upward on the planet of Mars with a velocity of 10 meters per second, its height in meters after t seconds is given by the equation. I guess they didn't write h of t, but I'm going to write it as a function in terms of t. Find the velocity of the rock after 1 second. So what's the relationship between a position function and a velocity function? It's not the same equation. The velocity function is the first derivative of the position function. So our answer here is just going to be the limit as h approaches 0 of h of 1 plus h minus h of 1 over h. Is that okay with everybody? Sergio?
Sorry, I got like spaced out for a second.
Uh-huh. So we're given a position function, a function for height. The velocity is the first derivative of a position function. That was something we talked about in our notes in 2.7. So that's why I'm taking the derivative here. And this is just the definition of a derivative at a point that I'm using. Is that okay?
Yeah.
Cool. So if I do this, I have 10 times 1 plus h minus 1.86 1 plus h squared minus the quantity 10 times 1 minus 1.86 times 1 squared. Forgot my limit. I'll just squeeze it in there. Mackenzie, so far so good? Yes? Okay. I'm going to notice that I can't do direct substitution on this. I really couldn't have done it even at the first step because you end up with 0 over 0. So I'm going to go ahead and simplify this all down as far as I can and hope that when I'm done, I can cancel some h's. So I'll distribute the 10. I'm going to FOIL out the 1 plus h squared. And then if I distribute through that 1.86, what's that gotta be? 3.27? I think it's 7.2, right?
Yeah.
Okay. It's early for mental math. So the 1.86 is canceled, the 10 and negative, or the 10s cancel. I notice that everything I have left has a factor of h in it. So I can reduce those. And now I can direct substitute. Oh, there. It's like that can't be right. There's what I'm missing. 10 minus 3.72 minus 1.86 times 0. So I get 6.28 meters per second. That's my answer there. Does that look okay so far, Mackenzie? This has a million parts to it, which is super lots of fun. Part B asks us to do this now rather than specifically at the point 1, but to do it at some general point A. Oops. Did the same thing. Just sneak that limit in there. Who's like, Mr. Hulick, this is so dumb, it's like the exact same steps as the previous problem? And I would say, yup, you got me. So let's see. Minus 10a plus 10a, those cancel out. Plus 186a squared minus 186a squared cancel out. I can reduce an h from everything. And then when I do my direct substitution, I get 10 minus 3.72a as my velocity. Now, given these two problems, which order would have been the better order to do this in? I would have done part B first. Because why? Once I had part B done, I could have just plugged 1 in for A to my answer to part B and skipped having to do that 2 times. Just me looking for an efficient way to do this. Just reminding you of the power of that, doing the derivative kind of generally like that, is that once you have that equation, you can then plug in values for A, any value you want. You don't have to take the derivative over and over and over again, which is a hassle at this point. It becomes less of a hassle here in a couple of sections when we start developing the shortcuts. So it asks then, when will the rock hit the surface? Well, you could do this 2 separate ways. So the rock hits the surface when the height is 0. And then, well, I guess when it hits the surface, that's really what you'd want to do. You'd want to do the height is 0. Let's not get cute about it, Mr. Kulik. So if I solve this for t, I can factor greatest common factor of t out. I apply the 0 product property. 6t. So I get t equals 0. Well, no doy, if we're throwing the rock up off the ground, initially its height is at 0, okay. And then if I do this one, I get 10 over 1.86. Whatever that is approximate to. I'm not feeling very ambitious to try to mental math my way through that one. It's got to be a little more than 537. So that's the one that I want. And then it asks, what's the velocity at that time? So all I'm going to do then is plug in 537 into my answer from part B. Oh, but Mr. Kulik, it looks like I'm getting a negative answer. Is that okay? Well, yeah, sure it would be. What direction is the rock falling, or what direction is the rock going when it hits the ground? It's going down, right? Which would have a negative velocity to it. So that certainly makes sense. So we got about negative 9.98 meters per second. Which is telling you something maybe about the gravity there, right? We start by throwing it up at 10 meters per second. It hits the ground going almost 10 meters per second still. That's kind of neat. Mackenzie, did you feel okay about that? It was really part 1 and part 2 that you just had to do some heavy grinding. They're kind of irritating. We'll stop being irritating in once we start chapter 3. I think we go straight into okay, enough of this. Can we do the derivative without taking a limit? The answer is going to be yes. This is one that particularly you could have done in your head in another couple of sections. Or the expectation you'd be able to do that derivative in your head without having to grind through all that nonsense. You should start with that. I know, but then you don't understand what a derivative is. And like, there's a bunch of like theorem and intuition stuff that you need to understand like how you're actually calculating these things. Because you lose all that if you just learn the shortcut. So the compromise is we're going to do it the long way for like 2 sections, and then we're going to stop doing it the long way because we've gotten all the intuition we're going to get out of it and stop being, let's stop being irritating about it. You know what I mean?
On the AP test, we'll do a short way.
Depends on the problem. It's very likely I've seen in the free response questions things set up so that like you have to kind of use the definition of the derivative to do it. Because either you're given something that's tabular or a graph where you don't have an equation to shortcut your way through it. But a lot of this stuff that they're giving you on the AP in the calculator section, you absolutely could shortcut your way through it, or calculator your way through it where you don't even you're not even doing these derivatives by hand. You're just like typing into your calculator and getting the answer out and using it to do something else. Okay. You guys feel okay here? Can we start 2.8 or try to finish 2.8 here? That's what I would like to do here. So we had, oh boy, let's just skip to here. So last time we had done some examples on, or what we had been doing in section 2.8 had been taking the derivative generally rather than focusing on a specific point like we did in 14a, or even with like a specific point but in general as we did in part B. Here we're going to use just in general. So if I want to find the derivative of f, we're going to do the limit as h approaches 0 of, well, maybe we'll write it, f of x plus h minus f of x all over h. Just FYI, this thing is called a difference quotient. I don't know if that's important or not to us, but I'm going to go ahead and do my substitution now. So I'm going to write this as with the functions filled in, but what did I forget? My limit. Oh no, what do I do now, Mr. Kulik? I can't direct substitute because I end up with 0 over 0, and I can't really simplify this and expand it out or anything. What should I do? Multiply by the conjugate. Yeah. It should be screaming at you in big, bright, bold, flashing letters. Conjugate. Conjugate. Is everybody okay? I skipped some simplifying when I multiplied the conjugate together a little bit. We're okay with the skip though? think that's probably okay for us. It's not the first time we've used that trick. I notice now that if I combine like terms, the x and the negative x can cancel out, which allows me then to reduce the h's. So I'm left with just a 1 on the numerator. So far, so good. And if I do the direct substitution here, I get 1 over 2 times the square root of x. Okay. All right. Taylor?
Is that all we're looking for? Like, it's just.
So that's the equation for the derivative, is that f prime of x is equal to, yep, so that's what the derivative is equal to. So I can use that to then find the derivative at any point I'd like by just plugging in the value for x into that function. Rather than having to go through that limit thing over and over and over again, I can do it once in general, and then I can just calculate as many limits as a point as I'd like at a point afterwards just by plugging them into a function, which is super preferable to doing it by
Creating like that's created like a formula for what it is.
yeah. So what the derivative does is it operates on a function and it returns back to you another function that you can use to calculate derivatives at a point.
So what would it ask when you're trying to like calculate a derivative? Like would it give you a number and you plug the number in for x?
Yeah, I would say, I mean, no. I mean, it could just ask, like, you know, find the derivative of the function, and then just give you the function. And if you're not given a point, you're doing what we just did here.
Yeah, but if you are given a point, you would just plug like the x into where the x is, and then that gives you.
You could absolutely do that. Or you could have done what we did in last chapter,
Okay.
like when we did part A here, where I did that limit of 1 plus h, so there's no x's in it. Or you could do it with the x and then plug the value for x in at the end. Either one is fine.
All right.
Whether you want to plug the x in at the start or at the end, either is fine. You're doing the same thing. Mia? Yeah, it's ostensibly the same thing. The difference is that I returned a function in terms of x, right? Like I have now f prime of x, which is a small detail, but yes, it is the exact same process. Okay. Notations. How many different ways do you suppose we have to represent a derivative? There's lots. So we could write it as like f prime of x. We've used that notation so far. You could write it as y prime. You could write it as dy over dx. You could write it as d over dx of f of x. I know, guys, right? You could write it as capital D of f of x. Or if you want to be really specific, you could write it as d with a subscript of x of f of x. These are all notations that at one point or another you'll probably see. And I know you're looking at me like, why the heck do we have this many stupid notations? And it's because all these notations, like pieces of calculus, were created kind of independent of the main body, because all this was happening like in the 16 and 1700s, before you had easy, rapid communication and sharing of ideas. So like when Russians figured out calculus, the notation they used, they refused to give up. It becomes accepted part of everyone else's notation. The French refused to give up the notation they were using. The Germans refused to give up their note. So like you just end up with all these different notations because these areas didn't really communicate to each other that well or that much, and language was a definite barrier. Like to read about mathematics happening in Russia, you actually had to speak Russian and be able to read Russian to read a paper. Which
it's not that deep, they could have given up the station.
Okay, let's all just learn Spanish then, right? Let's forget about English.
Well, it's like
Look, in the 70s, they tried to give up the English system and do the metric system in America,
Yeah, it didn't
and there was almost like an insurrection over it. People just refused to do it. And you think you're gonna, yeah.
But
It's the same thing.
It's not a whole system. It's just like, what's wrong with that?
No, there's like a whole associated notation that goes along with it.
Okay. So
Like
that's-
it just follows through.
Okay.
All right. So I'll start kind of mixing in some of these other notations as we go so that we can kind of get comfortable seeing these things then representing the same thing. Probably not right away, but the further in we go, the more that I'll probably start doing that. Particularly the dy dx notation is particularly useful. All right, we say that a function f is differentiable I guess I should say at A if f prime of A exists. We say that that function is differentiable on an open interval if it's differentiable at every point on that interval. So if we go back to that previous example we just looked at, where is f prime of x differentiable? On the open interval from 0 to positive infinity. Note that that is a different domain than f of x, which was differentiable on the closed interval from 0 to positive infinity. Because the x is in the denominator, right? Can't have a 0 denominator. The other one, the x is in the numerator, so 0 numerator, okay. Yeah. So notice here that x is not differentiable at 0, even though 0 is in the domain of f of x. Right? That's kind of an interesting observation. So this should lead you to a question, right? We've seen now a function that is not differentiable over its entire domain. Where could a derivative fail to exist? So, easy answer is some kind of discontinuity. So in the case of our square root function, right, we had a start. So like that would be a problem. If we have something like the natural log of x, there's an asymptote in there, some kind of discontinuity like that. Or if you had something like a step function where there's a jump discontinuity, any of these things are going to present a problem for us. Another place where we're going to have to worry about is when we have a vertical tangent. So what do we mean by that? So if you remember, like, kind of the canonical example is the cube root function. Right here, if we zoom in, what you're going to see is that the function kind of does this. Kind of does that if you zoom in enough. This is what we mean by a vertical tangent. If you try to draw a tangent line to the curve there, it's a vertical line. So you're kind of just looking for places where the graph goes vertical for just a split second. And not even expressly, it doesn't have to be all the way, it doesn't have to be vertical, actually, because we're talking about a tangent line. So you're talking about the slope at a point. So if you have just one point where the tangent line would be a vertical line, the derivative would fail there, since we know a function can't have a vertical component to it, right? And then the last one is a corner. So the canonical example for this is the absolute value function. So at that corner, the absolute value function does, or the derivative does not exist there. Why is that corner a problem? Well, if I look at the limit, and we'll write it this way, as x approaches 0 from the left of how do I want to say this? Where was that? I need to go back and look at that notation that I'm digging out to use. That's it. So this is the slope for that part of the line, right? Should be -1. And then this would be the slope for this part of the line. This would be positive 1. And what do you notice about the two limits? The right-hand limit and the left-hand limit do not match. What does that tell me then about the limit as x approaches 0? It doesn't exist. Yes, very good. And that was the definition of our limit. So if we can't, the limit doesn't exist there, our derivative can't exist there, since we needed the limit to calculate the derivative. So basically you're looking for, on these corners, you're looking for a place in the graph where the slope of the tangent lines from the left and the right don't match. Right? That's all we're really kind of talking about visually. Okay. So I've kind of mentioned this already, but you can take the derivative of a derivative. We call that the second derivative. So the notations there, we'd use like f double prime of x, or y double prime, or d squared y over dx squared, etc. So let's say our function was x cubed minus x, and our first derivative then would have been 3x squared minus 1. If I want the second derivative, well, it's just the limit as h approaches 0 of f prime of x plus h minus f prime of x all over h. So when I plug things in, I get 3x squared plus 6xh plus h squared minus 1 minus the quantity 3x squared minus 1 all over h. And then I'll just distribute that negative through, combining like terms, and then I can reduce the h's, so that would give me, oops, forgot to cross out that one too. So that gives me 6x, and when I do the plus 0, when I do the direct substitution, or just 6x. Everybody's okay with that? Oops. I missed, there was a 3 here. It didn't really matter because when we did the direct substitution, the 0 from the h destroyed it, but there should have been a 3 right there. My mistake, folks. Yes, Victoria?
Why did it, why did you bring x plus h?
I did. I just wrote it foiled out right there.
Oh.
I foiled and distributed all in just one step.
Oh.
Is that okay? Maybe I should advertise that better. I'm sorry, guys. So if I have a third derivative, the notation we're going to use there is just f triple prime or y triple prime or d cubed y dx cubed. So just using the same notation, just updating. So let's say we had this same f of x, and we know that the second derivative now is just 6x, and we want to find f triple prime, the third derivative. What do you notice about each time we take the derivative? What's happening to the function?
The degree is getting.
Yeah, it's getting simpler, right? Which is really nice. Yeah, the degree is decreasing by 1 each time. Which is super, super nice. What would we expect to get if we did the fourth derivative? 0. And then the fifth derivative? 0. And the sixth derivative? 0. And any derivative after that? 0. So eventually, well, depending on the function, if you do enough derivatives, it goes down to 0 because there's no rate of change going anymore. Mackenzie?
No, I was just gonna ask, is it presumed that it works out?
No, there's a product of this function type in particular. And there are functions where you can take an infinite number of derivatives and you're never going to get 0. Think for a minute about what that function might look like. What's a function whose rate of change is never constant at any point in the function? So if you think about like an exponential function like e to the x, that's one that you can keep taking the derivative of it and you're not going to get to 0. We'll look at that specifically in a moment. So remember back to physics, we've mentioned this before, but if we have some position function s of t, and we take the derivative, we end up with a velocity function. And we take another derivative, and we end up with an acceleration function. And if you wanted to do one more derivative, this thing has a name too. This is called jerk. It's not named after me. Oh, ha, 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 ha. So this is just a little bit of vocab. It's the same idea though, right? That we've just been doing. We just give, in a physics in physics land, we give a special name to the first derivative, second derivative, third derivative of a position function. Namely their velocity, acceleration, and jerk. All right. So the last assignment in chapter 2 is here. Next time we'll talk about test format and stuff. I'll give you some review stuff to look over. We'll probably do some practice AP multiple choice questions, answer general homework questions from you guys, and that'll be our day. And then we'll plan on doing the test the class period after that. So Monday, yeah. Does that sound okay? We can talk some more Thursday if you have problems. That's okay. We'll talk about it some more on Thursday. And I'll listen to all of your complaints and give them all the consideration that they deserve.
Uh,
Okay, that's fine.